That's my cue. Good morning, everyone. Thanks for making it out so early. I'm going to tell you today about some work that I've been doing in collaboration with Neil Agarwal at the University of Toronto, and it's been spearheaded by a hardworking graduate student that we share, Lee Yun, who you'll hear from in the next talk. And the work, if you're interested, the work will be coming out in proceeding speed, hopefully any day now. So it's generally thought that most genes in the genome affect an individual's health or vigor, what some people may say is their condition. And it's also thought that an individual's health or vigor is going to affect all its components of fitness, its viability, its fertility or fecundity, and their reproductive success. And what this means is that for most genes in the genome, an allele that decreases viability or fertility, non-sexual fitness, is likely to also decrease male reproductive success. Same thing for an allele that increases viability or fecundity is also likely to increase male reproductive success. So in other words, there's a general expectation that across the genome, sexual selection should align with natural selection to both promote adaptation and to aid in the purging of deleterious mutations. And this idea is old. It goes back to Darwin and the origin of species. Now, in the last decade or two, there's been a fair amount of empirical attention given to testing this expectation of an alignment of natural and sexual selection. And one common approach that's been used to test it has employed experimental evolution to track across generation either changes in components of fitness or the frequency of an individual beneficial or deleterious allele under alternate treatments that manipulate the opportunity for sexual selection. And so these treatments involve enforced monogamy, in which sexual selection is removed, largely removed, or polygamy, in which sexual selection is allowed to occur. And surprisingly, inconsistent with expectations under this simple hypothesis of alignment, quite a few of these studies have found no evidence of any benefit of sexual selection under polygamy. In fact, a couple of them inferred a potential cost. Well, it turns out that the contrast between monogamy and polygamy involves more than just altering the opportunity for sexual selection. It can also alter natural selection on females through its effects on sexual conflict. So this works as follows. Most people are probably aware that as a byproduct of competition for reproduction among males, that male sexual tension, mating, courtship, are harmful to females in many species, including Drosophila melanogaster. Now, in a seminal paper in 2009, there's a typo there, sorry, Tristan Long showed that given the choice, Tristan Long and colleagues from Bill Rice's lab showed that given the choice, Drosophila melanogaster males will bias their sexual tension in mating attempts to otherwise intrinsically better females, bigger, healthier, more vigorous females. And then by disproportionately allocating their courtship effort and matings to these females, it decreases the selective advantage because they experience disproportionate male harm. So some of this data is shown here in the figure where we plotted mean female fecundity, just focus on replicate 1 here, for large females in the filled circles and small females in the open circles. And the absence of any opportunity for males to choose between them, large females, not surprisingly, have higher fecundity than small females. But if you present a male with a mixture of large and small females, he courts, harasses, mates, and otherwise harms the large females, depressing their fecundity. And the small females are protected by the presence of these large females that draw the male sexual attention away, and so their fitness actually goes up. And they refer to this as a cost of sexual attractiveness. These large females are paying a cost of being attracted to males. And the population level manifestation of this cost is a reduction in the variance in female fitness, and thus a hampering of natural selection on females. Fecundity selection on females in this treatment is weaker than it is in the absence of this male differential harm. So under polygamy, the combination of male harm and male mate choice weakens natural selection on females. And this may offset any benefit of the addition of sexual selection in a polygamous environment, mating environment. Now, surprisingly, of those previous studies I showed you that failed to find any benefit of sexual selection in these evolution studies, experimental evolution studies, only 2 of them looked into why this might occur, and both of them inferred this cost of sexual attractiveness was occurring, suggesting it may be actually be an important phenomenon. Well, this is where Neil and I came in. Thinking about some of these results, we realized that these experimental studies almost exclusively use various species of Drosophila, and they're all done using standard Drosophila lab environments, a vial or a bottle in the lab. But these environments deviate from nature in some very systematic ways that may potentially be quite important. And then this may be influencing the outcome of the studies and possibly biasing the perspective of the field in terms of the importance of this cost of sexual attractiveness and its effects on the alignment of natural and sexual selection. So in particular, compared to a lab environment, the natural environment obviously has increased space and structural complexity, and both of these are likely to alter sexual interactions, their frequency, their duration, potentially the fitness consequences of such interactions. So we conjectured that polygamy in a standard lab environment may actually be exaggerating this cost of sexual attractiveness and hence weakening natural selection through females more than it would in a more natural environment. And this may explain why we don't see any benefit under polygamy of the addition of sexual selection because it's being offset by this added cost. And so we set out to test this. And to do this, we used two different physical environments during mating. So one was the standard lab environment, simple vial here. So this is high density, spatially restricted, and structurally very simple. It's just an empty glass or plastic vial with a bit of food in the bottom. And then we took a second environment, which, as Anil likes to say, is a micro step towards a more natural environment. We're not going out in the field here. This is a Ziploc container. You put your leftovers in the fridge, but it's 1.65 liters compared to less than 100 milliliters there. So it's order of magnitude or more, bigger in volume. It has multiple food patches here. These are paper cups with food in the bottom, little dividers on the surface of the larger cups there to further partition the food. Females can choose where to feed and lay eggs. There's places for females to hide, and then sticking down from the lid inside, you can just barely see, were some pipe cleaners. So there's some added structural complexity. Females can potentially escape male harassment. They have places to hide, and they have choices to habitats to feed and lay eggs. So we did 3 separate assays using these 2 mating environments. And all of these assays used a population that had evolved, that had a life cycle in the lab that included a 6-day mating phase. So we could manipulate that mating phase to occur in one of the other environments, and after which females got 24 hours to lay eggs. So it made it easy to measure female fitness. So the first assay, we sought out to test the effects of the physical environment on the frequency of male sexual attention behaviors that were directed towards large versus small females. So the design was quite straightforward. We made large and small females via larval density manipulation. And then we took the adults and we put 34 males together with 34 females. Half of those females were large and half were small. And we did that either in this larger complex environment or the smaller, simpler environment. And then over the next 3 days, we did spot checks. And we monitored the amount of sexual attention 2 focal large and 2 focal small females were receiving. And they were marked simply by some fluorescent dust so we could identify them. So the results here plotted on the x-axis is the number of sexual interactions a female experienced, given it during a 1-minute period. And if you just focus on vials, we recovered Tristan Long and colleagues' previous result. That is, large females were attracting significantly more sexual attention than were the small females. But if you look in the cages, that effect entirely disappears. Large and small females are now no longer differing in the amount of male sexual attention they're attracting. Now, fecundity in female Drosophila is strongly dependent on the amount of live yeast they can feed on. So we also recorded how frequently we saw females feeding in these spot checks. And if you look in vials, surprisingly, small females were actually feeding at a higher frequency than were large females. But in the cage, this didn't just vanish, it completely reversed. So now large females were feeding substantially more frequently in the cages than they were in the vials, where small females didn't really change their feeding rates. Suggesting that in the cages, these large females were getting much better access to food than they were in the vials. So physical environment mattered, and it mattered in a way that it mattered in terms of the amount of sexual attention and feeding opportunities that a large versus a small female groups had. The second environment set about to test the effects of these physical environments on the extent of male-induced harm. This involved the 2x2 factorial design, which we manipulated male exposure, low versus high, and we manipulated the physical environment again, simple vials versus more complex cages. So under high male exposure, 35 females were confined continuously with 35 males throughout the entire 6 days. Under the low exposure, so let's just say 35 males were added to the container for a 3-hour period, roughly every 2.5 days. So female had access to sperm to reproduce, but males weren't continually present harassing them. And we did this in vials and cages. We recorded female survival over the 6-day mating phase, and then we recorded the fecundity of the surviving females. So here I've plotted adult female fitness, that is the product of their probability of surviving times their fecundity if they did. And we see that in vials, there's substantial male harm. Low exposure females, fitness is substantially depressed, and the fitness of high exposure females is substantially depressed relative to that of the low exposure females. And so that difference is the extent of male harm, and that difference, again, is substantially reduced and is no longer significant in the cage. So males are much less harmful to females in these cages than they are in the vials. So physical environment during mating, again, matters. And it matters in terms of the harm females experience. Finally, we set about to test the effects of the physical environment, how the physical environment alters the effects of male mate choice on natural selection. That is, this cost of sexual attractiveness. So again, this is a 2x2 factorial design, except now we're manipulating the opportunity for male choice, like Long and colleagues did in their previous assay. So under the choice situation, 34 females were combined with half large, half small females, so they could choose who they wanted to court and harass. And in the no choice, 34 males were combined with either 34 small or 34 large females. So they didn't have a choice in terms of who they're going to, the size of the female to which they're going to direct their sexual attention. And we did this again in vials and cages. We monitored, again, female survival over the 6-day mating phase, and then the fecundity of the surviving females. And from these fitness estimates, we could calculate selection coefficients that quantify the cost of females of being small, selection against small size in females. So here we plotted the selection coefficients. If you just focus on the top left here, this is viability selection. You see that all the coefficients are positive, which means there's selection against small females. In vials, here on the left, the addition of male choice, as consistent with what Long and colleagues previously found, significantly weakens selection on female size, as before. But in cages, not only does that result, not only does male choice no longer weaken selection, it actually strengthens it. And we have some ideas as to why the strengthening may have occurred. I'm happy to talk to anyone about that after my talk. Now, there was also fecundity selection against females in all these treatments, positive selection coefficients, but it didn't vary between vials or cages or choice or no choice. Now, if you take the product of those two to get total fitness, total adult fitness for females, what you find is that total selection against females was not changing in vials under male no choice or choice, but in cages, the addition of male choice under polygamy was significantly strengthening the selection against the females. So the complete opposite result to what Long and colleagues previously found in vials. So what do we conclude? It seems that at least in Drosophila and Melanogaster, polygamy is less likely to impede natural selection on females when the environment is even slightly more natural than is a typical lab setting. And we attribute this to the effects the physical environment has on sexual interactions, which we showed are in cages are less frequent, are no longer biased towards large females, and are less harmful to the females. However, we can't entirely rule out other effects that these different mating environments could have, which may alter how male choice affects selection in females. These cages differ in the material they're constructed out of, differ in food availability, things like that. But overall, our results suggest the physical environment may play a key role in determining the alignment of natural and sexual selection. And it may help to explain why past studies that have used a monogamy-polygamy manipulation to test the idea of alignment may be failing to find a benefit. Any benefit of the addition of sexual selection or polygamy may be offset by this large cost of sexual attractiveness. And so with that, I guess I have 1 minute per question.